this concept is pretty neat. You do need to go slow and pay attention to exactly the right layout of each triangle in order to make sure you're orienting them correctly. But this is what it says. When you draw the altitude to the hypotenuse of a right triangle, you form three pairs of similar right triangles. What does it mean to be an altitude? It's going right from that vertex where that 90-degree angle is, perpendicular to the opposite side, okay? That's the altitude. And when you drop that down there, you get a smaller triangle here, or this triangle here, and then a large triangle, and you need to orient them correctly. You can see that this one is actually flipped into place there, as is this one, okay? Then you get this feature going on, okay? One good way to do it is to think of these as the hypotenuse of each of those two smaller triangles, and this is the hypotenuse of the longer one. Make sure that those are lined up, and you have a shorter side here in this case, and a shorter leg, I should say, and a longer leg. Here you have a shorter leg and a longer leg, right? And this is the shorter leg of the big triangle, longer leg of the big triangle. So be aware that you're lining things up correctly. Anyway, if triangle ABC is a right triangle with right angle ACB, and CD is the altitude to the hypotenuse, then you get this relationship. Here's a proof of why this works. I'm going to let you pause it and read through it as you like and ask me questions if you have them. I'll just keep moving with the lesson. But here's an explanation so you don't have to just take us at our word that this is true. So here you can see that we have a right triangle that has an altitude dropped. So we've split it into two smaller triangles. They're asking what similarity statement can you write relating the three triangles in the diagram. And it's hard to kind of see because you don't have it all oriented correctly. So what will help you see what corresponds is maybe sketch them separately, labeling the vertices and sketching them in the correct same orientation, okay? If you try doing that, let's see what we get. We see that YW is the altitude, so we can use theorem 7-3. There are three similar triangles. We already kind of knew that. And here's how you do it. You can take that larger triangle, label the vertices, X, Y, Z, and then take this triangle, and you can see that that 90-degree angle W has to go down there, and this smaller acute angle is Z, that's there. Y is going up, right? So that's getting flipped. This one as well, it's getting flipped. That right angle W going there, and that top vertex X there, and this pointed smallest angle Y. Now it's all lined up, and you can then write it as triangle XYZ going from here to here, similar to triangle YWZ, is similar to triangle XWY. Yep. Okay, so here's your got it problem. What similarity statement can you write relating the three triangles in this diagram, similar to this? And then also, from the similarity statement in part A, write two different proportions using the ratio SR over SP. SR is the longer leg of this triangle, over SP is the shorter leg. So if you do it with the other two triangles, longer leg over shorter leg, you should be able to, and you can use the similarity statement you wrote to do it. You should be able to write them as a proportion. Yep, try that. All right, now we're going to be talking about the geometric mean here, okay? There's proportions that you can write where the means are equal. We have the extremes and the means is how we define them. Remember, the extremes are the highest and lowest numbers in a ratio. For example, if you were to say, let's say 2 over 6 equals 3 over 9, okay? These two numbers are the extremes in terms of being the lowest and highest number, okay? We're gonna just keep that in mind for a second. So if you look at that here, you say some proportion has these two extremes as lowest and highest number, and the geometric mean is essentially the square root of their product. So there's the same number you could put here and here, where if you multiply those together and you multiply these together, they would be equal, okay? So essentially, the square root of a times b will be the geometric mean. Why does that matter? Because when we have triangles written in the way that we're dealing with them, you're going to see the proportions set up where you get the same number here and here. And if you need to find that number, it is the square root of these two multiplied together. Okay. So what is the geometric mean of 6 and 15? Well, what do? You multiply them together and you square root them. Okay. What do we do when we do that? Well, again, set up a proportion with x in both positions. Okay, so it would be like 6 over x equals x over 15, for example. Okay, so 6 over x equals x over 15. You can see that x's are diagonal from each other, and 6 times 15 is 90. So you get the square root of 90 is what x is equal to. And if you know anything about writing square roots here, you can essentially expand square root of 90 to be the square root of 9 times the square root of 10. And you can take the square root of 9, that's 3, outside. And then that's what you get there. Okay, I can go into more detail about that if you needed some coaching on how to do the square root of a number that's not a perfect square. Anyway, what do you get? You get the geometric mean of 6 and 15 is 3 root 10, because 6 times 15 is 90, and you do the square root of that and simplify it. Okay, try this one. What's the geometric mean of 4 and 18? So as I said, this is going to come up in these types of problems, and this is where it comes up, okay? Used a pair of triangles to write a proportion with the geometric mean. Notice this, if you're doing this triangle to this triangle, right, or this triangle to this triangle, what you've got is short side. This is the long side of one triangle. It's the short side of the other. So if you say, so short leg on the blue one to the short leg on the green one equals the long leg on the blue one to the long leg on the green one, what you get is that same side length, SP, diagonal. That's where this comes in, okay? So you'd say that times that square rooted would be whatever that was, right? So that illustrates this first of two corollaries. It's theorem 7-3. So it says the length of the altitude here of a hypotenuse of a right triangle is the geometric mean of the lengths of the segments when you drop that altitude. So this hypotenuse of the big triangle is split into two segments, AD and DB, when you drop that altitude. The geometric mean of that, or this times this and then square rooted, is what the altitude is going to be equal to. Pretty neat. So in this case, let's say you drop this altitude and you get 2 here and 8 here. 2 times 8 is 16. The square root of 16 is 4. That's what that altitude is. Neat. Let's take a look at what we get with the second corollary for theorem 7-3. Okay, so this corollary, it's easy to get confused. I'm going to try and just sum it up for you, okay? If you take the large triangle's hypotenuse, in this case 4, times one of the two segments that's formed by the altitude, in this case 1, you multiply them together, 4 times 1, that's going to be equal to that same side, that triangle, this segment came from this triangle, so that hypotenuse squared. So that squared equals this times this. The full hypotenuse of the big triangle times the length of the segment that's formed by that altitude, that times that, equals that squared. That's the basic idea there, okay? Now, corollaries to 7-3 give ways to right proportions using the lengths in right triangles without thinking through the similar triangles. You can just kind of set it up without having to lay everything all out, which triangle is which and all that, okay? To help remember these corollaries, consider the diagram of and these properties, okay? You can say this is the full hypotenuse and leg 1 and leg 2 for the big triangle, right? This is the altitude, and this is segment 1 and segment 2 formed when you drop the altitude, okay? So then you can have this. Segment 1 times segment 2 equals the altitude. Segment 1 times segment 2 equals the altitude squared, altitude squared. And you also get this, where leg 1 squared is equal to the hypotenuse times segment 1, coming from both from that same triangle over there. And the hypotenuse times segment 2 is equal to the leg of that one, that hypotenuse squared. So take these as notes. Now, we're obviously going to apply this. So if you took those notes, that, like I told you to, you have those written down and you can calculate these out. What is the value of x and the value of y? And let's do this in two parts. I'm just going to talk you through to remind you. Remember, this times this segment times this segment equals this squared. So what is 12 times 4? 48. The square root of 48 is what y is, okay? And you'll get that broken down in a second. Here, this one is going to be this entire length of 16 times this 4. 16 times 4 is 64, so this will be 8. Now, let's see it in action. Oh, by the way, they make a note up here. If you're using or finding an altitude, use corollary 1. And if you're using or finding a leg or the hypotenuse, use corollary 2. We used them both just now, but let's see how this breaks down. Oops. Okay, so for x, we're going to use corollary 2, where we do this whole length here over this equals this over that. And you see that we do get 64 square rooted for 8. Here, we get the altitude squared equals the two segments, or square root of 48. And this breaks down, if you don't know how to break this down, just as a quick note, because you should do it, you should be able to break down using a factor tree, 48. And when you list the factors of the prime factors of 48, you get 2 times 2 times 2 times 2 times 3. And then you're looking for pairs to bring outside. That's a pair, you bring a 2 out, times this is a pair, you bring a 2 out. And so you multiply them back together and you get here 2 times 2 is 4. That's the 4 out front. And this is the 3 that didn't have a match that's still inside. Okay, that's how you do that. Yeah, using the proportions that we just learned. So try it now with this got a problem. All right, this is a great one because this is a cool application of this and you really need to kind of puzzle out what you're trying to do here. But you're preparing for a robotics competition using the setup that's shown here, and points A, B, and C are located so that AB is 20 inches and AB is perpendicular to BC, meaning that we've got a right triangle here. Point D is located on AC so that BD is perpendicular to AC. Now we've got that altitude drop down. We know it's an altitude because it's going from the vertex at that right angle of the right triangle, perpendicular to the other side. Okay, and we know that DC here is 9 inches. Okay, this is X. So if we were going to program the robot to move from A to D and then pick up that plastic bottle, how far does the robot have to travel from A to D? Well, puzzling it out, we say, okay, remember when we're dealing with legs and hypotenuses, what we want to do is the corollary, corollary 2, which is that you take, this hypotenuse over this hypotenuse, right? X plus 9 over 20, okay, equals 20, the long leg of the big triangle, over X, the long leg of the triangle here, okay? So the full length times that will equal that squared. Yep, or that times that equals that times that. That's the setup. And then we use the cross products property. When we do this, though, we get this. And what can we do here? We can't solve it by taking a square root, so how do we do it? We write it in this form, quadratic formula, subtract 400 from both sides, so we get x squared plus 9x minus 400 equals 0. And then we have to factor. This is something that's a skill that's going to keep popping up at you until you figure out how to do it. So when you do that, you factor this out. You say what two numbers multiply to be negative 400 and add together to be 9. These two numbers multiply to negative 400 and add to 9. okay? So setting each to 0, because the zero product property says if you're going to multiply and get 0, one of the things had to be 0. So either this was equal to 0 or this was equal to 0. When you solve that, you get x equals 16 or x equals negative 25. And there's a fun fact going on here that only positive solutions make sense because we're dealing with a length, and lengths are always non-negative. So the robot travels, whatever the positive value is, 16. And we know the units was inches. Yep. Okay, from point D, the robot must turn right and move to point B to put the bottle in the plastic recycling bin. How far does the robot travel? What is that altitude? So that's the lesson. It's pretty neat. Take notes, keep track of things, do these lesson check problems, and see if you know what's going on here. You can jump right into the homework, but just give it a go. It doesn't hurt to do a few extra problems as you know, and then when you get to the homework, you're not guessing and checking because you're working it out first by just seeing what you know. Good luck.